Thank you for being here. How's everyone doing? How are the sessions? How are the open spaces? Yeah, good to be back in person. This is my first in-person talk, so I'm really excited. I hope you all had a good time. Today, my name is Adarsh Shah. Today we are going to talk about something new as code. We have so many things as code. Today it'll be environment as code. This talk is basically based on my and my team's experience, kind of working with infrastructure as code and cloud native tools over the years, and what are the various challenges we have seen implementing or building a platform or automation for various companies, from enterprises to startups. So some of what you hear about environment as code is kind of new, and I would love to hear what you all think. If you have any feedback, if you want to discuss further, I'll be around. Let's get started. All right, so I'm going to go through a couple of terminologies just to make sure that when I say them, you understand what I mean. First one is components. So when I say components, what I mean is a logical grouping of one or more infrastructure resources or applications. So one of the examples is networking. If you want networking, you want your VPCs, your subnets, your internet gateways, and route tables. So as a group, I call it components. And then when we say environment here, that's the logical grouping of multiple components. So it could be networking, your EKS cluster, your databases, your Kubernetes apps, all of that, whatever is a meaningful grouping for you, that'll be environment. So we all know what infrastructure as code is. It enables teams to deliver infrastructure and thereby software running on it rapidly and reliably. And here's how I see an evolution of when you start using infrastructure as code. You probably are one or two developers who do some POC. They kind of write some monolith ISE that provisions your networking, your EKS, what have you, and you test it out locally on your laptop. Things work good, and then people love it. Other developers want to use it or they want to run it. And then you start kind of feeling the pain of there are so many different components, right? I want to break my ISE into multiple separate components so that it's not a one monolith ISE with a massive state file if you're using Terraform. And then if you have Helm charts for your apps, same thing. You want to break them into smaller pieces. So yeah, like here, as you see, you have multiple Terraform components, and then you have your apps with Helm charts. So this talk is for folks who have already started ISE, or they are looking to do so, or at least a little bit advanced, where they are looking to at least break those monolith ISE into smaller components. And then here's how I see an ISE execution evolution, right? So again, you start by running stuff on your machine, and then eventually you look into writing your ISE pipelines or using GitOps way to kind of provision in a shared environment, right? So your laptop might have certain dependencies or certain version of Terraform, but you want to run it in a common shared environment like a pipeline where you have more reliable setup. So again, when I say environment, this is an example of an environment where you have a bunch of different components put together, and that might be a production environment where you have networking and EKS and database and SageMaker and all that stuff. So what are the current options if you want to provision an environment like I just showed? Again, you can either write a monolith ISE, create a pipeline, run it. Works well if you have a really simple setup. Or you hand roll all these pipelines. And when I say hand roll, so let's say you are using Circle CI and you're doing pipeline as code, you write all that code and I have seen that code get really messy. Basically, we at one place, we had like 1,000-line code to provision 4 different environments, and then logic to tear down where you want to run things in, different order. You want to start at the leaf node, destroy them, and go up the chain. And all those managing complex dependencies and secrets and all that, those pipelines become really complex. So those are the 2 options currently, is what how I see it. And they are not scalable. It's once you start getting into more complex environments, it just becomes very difficult to manage. So what are the other challenges when you scale ISE? Replicating environment is a pain. Let's say I want a performance environment where I can run my performance tests. And it should look exactly like production, but a separate environment. Again, you have to go through, copy your ISE code and write pipeline or change pipelines. It's a lot of work. You can't visualize or understand environments. How do they look? Sure, you have everything as code. You can go look at your Terraform or Helm code. But again, there are so many various pieces you need to look at and put together to understand how they look. Drift detection. I mean, yes, Terraform, when you run Terraform, it tells you if stuff is drifted. But how do you know that my production, if you want to answer a question like, is my production environment exactly how I want it? There's no easy answer. You have to look at a bunch of things. You might have to run Terraform multiple times. Now for apps, if you have Kubernetes apps, sure, Kubernetes does that for you and it reconciles your changes. But for your infrastructure, you don't get that same kind of drift detection or reconciliation, basically. And the last one is, and someone actually mentioned in one of the open spaces, is it's not straightforward to promote changes, right? You can do GitOps, you can have all your Terraform and Helm charts in Git, but there are so many different places you have to look at. And if you're promoting changes across environment, there's no single pane of glass to kind of see what has changed and how those changes look. So these are some of the other challenges we have seen while scaling ISE. So what is this environment as code, right? Like, what the heck it is? So here's how we see environment as code. It's a declarative layer on top of all the other cloud native tooling, right? So you have your ISE, Terraform, and Pulumis of the world, and then you have Helm charts and customizers and serverless apps and all that stuff. What we are saying is we need another abstraction layer that kind of puts these various components together and builds something meaningful. And it is declarative. Currently, people do kind of define this how to run in pipeline. Pipeline code is not declarative. Environment as code is. And when I say declarative, you say what you want, and the tool just makes it happen, right? You get that with Terraform and with Kubernetes, but you don't get that with your pipeline code. So, yeah. And then, yeah, obviously, it all gets provisioned or deployed on your cloud provider or Kubernetes cluster. So, yeah, here's another way of looking, right? So again, a top abstraction layer, which has, environment as code, and then you have a bunch of your cloud native tooling that comes under that, and then you have your cloud providers and platforms under that. So yeah, here's another way of looking at it with taking Lego as an example. So on the left, you can see that how I see infrastructure as code is, especially for complex environments, is it automates various Lego pieces, right? So your networking, your EKS, various infrastructure resources and components. What environment as code is, it allows you to connect those various Lego pieces and build something meaningful, a Lego toy, which is your environment. And that Lego toy will be different for everyone, right? Your environment might look different than someone else's. So yeah, that's what kind of, if you look at it as a Lego analogy. So here's a definition. I'm going to quickly read, but actually focus on a few different things. Again, abstraction over cloud native tooling. It's declarative, so you just define what you want, and then the tooling makes it happen. And then, there is a control plane involved, which we'll look into. It's kind of based on the same concept as Kubernetes has a control plane that manages your apps running on Kubernetes. Similarly, for managing your environment, kind of having a control plane. It kind of does things like drift detection and other things. So now let's dive deeper into that diagram that I showed, and this has the control plane part as well. So again, you have your declarative environment as code, you have it in your source control, and let's say you're provisioning an environment, you have a control plane. Again, it could be a Kubernetes operator or something running on Kubernetes, and it manages something that we are calling environment state, similar to what Terraform manages Terraform state. What that manages is all your various dependencies. So run the networking first, and then kind of run EKS and Postgres because you need networking before you get those. And then once you get your Kubernetes cluster, kind of deploy your applications, right? Your Helm charts, run those. So it kind of manages those dependencies, what the status, if something fails, let's say EKS fails for some reason, it knows that networking was provisioned, EKS wasn't, and then when you rerun it or reconcile, it kind of keeps, the control plane actually does that. It detects any drift, it kind of does that for you. So that's the provisioning workflow. If you want to tear down, right, again, you don't have to write all that logic. You can just, in your environment as code, and I'll show example format, you can say tear down true, and the control plane knows what to do. It'll start kind of destroying stuff at the bottom. So destroy all your applications in Kubernetes cluster, then destroy your EKS and Postgres and networking, especially if you have ephemeral environments where you want to spin up stuff at 9 o'clock in the morning, and when you're going home at 6 o'clock, you can bring that whole thing down. It is a lot, it's very complex today with existing tooling to achieve something like that, because you have to write a lot of logic. With environment as code, it's pretty easy. So what are the various attributes of environment as code? Here's an example of our format of environment as code. Again, when I say our format, it honestly could be anything that describes your environment. And as you can see in this example here, what you will see is we have various components. You have some information at the top. By the way, this is custom resource definition in Kubernetes. That's what we use. And then you have team name, environment name. You see that tear down false flag and stuff like that. But if we focus on that highlighted portion, it says, give me EKS. Type is Terraform. I want to use Terraform. And this component depends on networking. And here's my source. Here's my Terraform module or my Terraform code. I want to use the VPC ID that actually was provisioned in my networking component. And then here's my variable files, right? So it kind of provides you the data for that component. Now, the other example here is once you get EKS, I want to actually use Helm for all my Kubernetes apps. So in that case, you specify type Helm, and then again, it depends on EKS. You specify where your Helm charts are, and then boom, you basically should, this definition should be what you need. Once you define this, push it, the system kind of processes it and kind of gives you that environment that you want. And then you see that flag teardown false. If you do that teardown true and push it, it should bring down the whole system. So another attribute is it enables or encourages actually teams to have this loose coupling, right? Again, you can write a monolith ISC, but by having this capability, it encourages people to have loose coupling, have smaller components that are basically could also be owned by different teams. So let's say for bigger orgs, if you have a networking team, they might own the networking layer and might write the Terraform for networking versus there's another, like app devs could deploy the Helm, write the Helm charts and deploy stuff. Again, it manages state for entire environment. So for example, what operation last happened, again, it's kind of similar to how TF state is, but basically it has the operation that happened last, and what's the status? It is success or fail, and it kind of manages that at an entire environment level, and then also manages at various component level, so that you know, if you want to know whether my environment provisioning was successful, you can just look at that and kind of get that status. So yeah, idempotency and immutability, a couple of attributes that are core to infrastructure as code. Why not get that for an entire environment, right? So, and for those who don't understand, I'm going to kind of explain what that means here. So on the left, you see that you define your code. You say, I want 3 VMs. In non-idempotent code, when you run that same code second time, it actually gives you 3 new VMs because it doesn't know what the current state is. Every time you run, it'll just give 3 VMs, right? And that's not what you want. You want 3 VMs. So in case of idempotent code, which is what Terraform and Pulumi and those tools do, you specify what you want. It gives you those VMs. If you reapply the same change, it knows that you already have the VM, so it's not going to provision it. So it gives you the expected 3 VMs. Now, what I'm talking about here, and this already happens with ISE tools, what I'm talking about taking up to that whole environment, right? So if I want to answer a question, do I have what I declared in my definition for my entire environment? With pipeline code, you cannot do it today because, again, those various pieces, the pipeline code is not declarative. Another immutable infrastructure, right? So what I mean by immutable, so if it's a mutable infrastructure, you basically make changes, and when you apply those changes, so you see that it's V1, version 1 of your infrastructure or apps, and then if you apply that change, you apply and deploy those V2 version on the same infrastructure. On the immutable side of things, though, if you make a change and you want to provision 3 VMs with version 2 of your code or infrastructure, it'll provision brand new VMs, right? So you don't keep long-lived infrastructure because you can have drift detection and over a period of time, things drift and stuff like that. So yeah, and then you basically route your traffic to the new VMs that were provisioned, and you get rid of the old one. So in case of immutable infrastructure, your infrastructure is not long-lived, which is a very key thing to achieve. If you achieve that, that's pretty good because you avoid a bunch of issues if someone made manual changes and stuff like that. Another attribute is visualizing and understanding environment. So now, this is an example from our product, but the key point here is you have all this information. If you think about the state file that was there, that tells you what's the status of your entire environment, individual components. You can even have other things like cost calculations and other things, and then kind of show all that information and visualize that in a way that makes sense. If I want to know how my environment looks like, how my prod environments, I can go to that one place and I can see the status, what happened, what changes. You can have auditing and other things built on top of that, but this gives you a visual of what an environment looks like. Another thing is drift detection. So again, it happens if you run Terraform today or Pulumi, it tells you there is a drift if there is one. But what I'm talking about here is, can you answer a question, is production is same as what I defined in my configuration? And it's very difficult to answer that question. And this is kind of same as what Kubernetes controllers do, right? They have this control loop, and if your apps go out of sync, the Kubernetes controller will bring them back to the desired state. So what I'm talking about here is taking up notch and kind of saying, can the entire environment be done that way? Now, you will see at the bottom, I say preferably with approval step that shows the plan. So for example, if you have Terraform and someone changed something manually or an indirect change in your cloud provider, you don't want to just revert back changes to the desired state if it is infrastructure, because that might involve destroying a resource, because sometimes changing stuff, so you preferably you should have a plan. You see the plan, you see that, oh, something's changing, maybe destroying and creating a new one, but you know what changes are happening, and then you might need an approval step before you bring that back to desired state. Other changes, other kind of attributes is comparing and promoting changes across environments. So as I mentioned, and in that definition, you see it's all file-based. You define what an environment looks like. You push it to your source control. You can compare those changes using source control, or you can use other tools to make it easier to compare. And then also promotion is easier, because now you're not looking at 10 different files at 10 different places, but you're looking at one abstraction layer at the top that will tell you what version of networking is deployed and what version of EKS or your apps are deployed. And that can act as a place where you can say, now I want to promote from dev to QA, the same version I have in dev. I can look at the dev config at one place and say, oh, we actually updated the EKS version. And here's why the version of new module is 1.2. And you make that same change in your QA and then to production. So it makes it easier to promote changes as well. And then, yeah, you can use GitOps, but not just for your individual components, but for an entire environment. So what I mean by that is, let's look at this example. So yeah, on the left, you kind of push your ISE code. You can even create a pull request, go through the GitOps process. You can run your maybe plan or something that shows you similar to what Atlantis and other tools do, but this will kind of do it at an entire environment level. Once you do that, someone looks at it, you can run your tests maybe here, and it could be anything like Terra test or one of those frameworks, or you can also for your Helm charts there is testing, so you can do some of that testing. Once that happens, one of your teammates looks at the PR, everything looks good, they approve it, they merge it, and once that's merged, a kind of control plane takes over. So control plane is observing your Git repo, let's say, similar to what kind of Argo CD does for your Kubernetes apps today. It observes it, it picks up the change, and it says reconcile the change, which will basically give you what you want, right? So all of this kind of being in a GitOps way. So you get auditing, you get someone to review and approve the changes if you want. And if you have teardown, let's say you want to tear down the whole environment because you want ephemeral environments, it'll be the similar flow. You make a change, in this case, maybe one single line of change that says tear down true, and then the whole thing will happen and you go through the process. So this way you get all the benefits of GitOps as well at an entire environment level. So yeah, that's the talk. Basically, something I would like to hear from you all. Does it make sense? Have you had these challenges? If you're scaling your ISE, did you actually face these challenges where you had to write a lot of pipeline code or bunch of other scripts that actually ran those individual pieces? Any other issues? The slides and some other details are at that bit.ly link, or you can even actually scan that barcode and it will take you to the page that has all the details. So yeah, that's the talk. Thank you folks for listening, and any questions, let me know.
Not a DevOps professional, but could you give a clarifying example of drift?
Yeah, so one example is, let's say there is a production issue or an environment has something going bad, and one of the engineers goes to your AWS console and makes a manual change because they want to fix something or they are trying something, and now that change is lost. So when you define something in your code and push it to Git, that's the desired state. An actual state is whatever is in your cloud provider or your Kubernetes. And if you want to detect that, that's what basically the drift is. Similar, like Kubernetes, what it does is it automatically remediates, like it reverts the changes and brings it back to desired state for your apps. That's what's missing in the whole environment, basically. Any other questions?
How general or specific do the declarative statements in the environment get?
Yeah, that's a very good question, and that is the challenge. I mean, so the example that you saw is basically what we do is we have types, component types, and if it's Terraform, we kind of provide a way to define, let's say, a Terraform module or variables or dependencies or whatever. If it's Helm, kind of similar where the Helm chart is. But we have also started facing that problem. So what we are thinking is kind of even breaking that and maybe say, here is your kind of settings file for your Terraform, and it'll have all the stuff that you need. For Helm charts, same thing. And then tomorrow, let's say we have Pulumi that you want to support, or other tools that come up like AWS CDK or what have you. So yeah, it definitely is challenging, and that's why we want to keep it generic enough so that you can cover everything, but you also have a way to specify specific things that you need for those types. So yeah, for now, we started by everything in that YAML, for example, but eventually it might make sense to have separate files that are specific to those component types. Yeah, it's still kind of, like I said, it's early stages kind of in a way, but yeah. Awesome. Thank you, folks.